Okay, hello again everyone. This is the powers and indices presentation. What you're looking at here on the first slide is the cube root of 493,039, and I can straight away tell you that the answer to that is 79, not because I'm cheating or I've worked it out at all, but because there's a special little trick which I hope to get yourselves to learn, and also I hope to be able to explain how you can teach it to your students so they can cube root any 5 or 6 digit cube number. It's a lovely little trick. It's not part of the syllabus, but it's good fun to teach them. I find it often inspires the students to improve their arithmetic, and they're always really pleased with themselves when they can do something like that, something which looks as difficult as indeed it does. So let's just quickly take a look over why basic arithmetic is important. Well, although it certainly doesn't occupy the same privileged position that it once took in the classroom, and I'm talking about sort of 30 or 40 years ago, it is still nonetheless very, very important. There is a movement in the mathematical community recently towards this idea that arithmetic isn't the be-all and end-all, and I would certainly agree with that. But that said, pretty much every mathematician will tell you that, being quick with numbers, with tables, with powers and roots is really, really, really useful if you want to ever become really very good at the subject. So well worth students getting the hang of it. The second thing I would also like to argue is that committing to memory numbers is not by any means beyond any student. In fact, I particularly recall a moment in my career when a student from a bottom set class in the local comprehensive, she found maths really jolly difficult. She had a particular set of special learning needs where she found shape and space actually incredibly difficult. But anyway, her tables were lightning fast, and I mean much, much, much faster than the students I teach nowadays in top sets or even in A-level classes. Her tables, she just knew them, and once you know your tables, there's no thinking involved when somebody asks you what 6 sevens are. You just know that it's called 42. I would always argue as well that it's no different to learning a list of names in a class. If you have to learn 30 names in a class, which you will do, and you'll have many classes of names to learn, that is no different to learning your tables, and anybody can do it. Now, I've always found the best way to achieve this is by leading by example and showing them, arithmetic in the classroom, showing them times table understanding, and routinely testing them, because there's only one way to learn it, and that is to practice it. So, what do they need to know? Well, learning the first 15 square numbers and the first 10 cube numbers is what I suggest you do. I would say to them that they certainly need to know the first 10 squares and the first 5 cubes, but it's nice if they know the first 10 cubes actually as well, and they will need to know the first 10 cubes if they want to do rapid cube root extraction on 6-digit numbers. Okay, so let's have a look at the square numbers first. So there we have a little table of n and n squared right the way down to 15. There are actually lots of nice little patterns in that table. Okay, so most of the time the students pick up on the fact that it goes +3, +5, +7, +9, +11 down the right hand side. That can often help people to, recall the next square number from the last one. But even more than that, I'd like you to notice that we have like 14965694140149665 on the units column. That's going to come in handy when I ask you my next question, which is, only one of the following 6 numbers which I'm about to give you is a perfect square. All a perfect square means is a square number. They will call it a square or a perfect square possibly in the question. But I'm going to give you a list of 6 numbers, very long-looking numbers. Only one of them's a square number. I wonder if you want to quickly pause the video and try and identify which one of those 6 numbers is the square number. So I hope you've given yourself a chance to identify it. If you haven't, keep it paused. But okay, here is my answer. Well, hopefully you'll notice that out of those 6 numbers, we've got them ending in 2, 3, 7, 1 and 8. Okay, now look back at your square number table and you'll notice that the first 10 square numbers only end in 1, 4, 9, 6, 5 and 0. Now I can immediately deduce that no square numbers end in 2, or 3 or 7 or 8. Because if you think about it, once you get past the first 10 square numbers, let's say we're dealing with a square number 67, when I square that, I know it's going to end in a 9. Because forget the 60s, the 7 times 7 is going to give you 49, and therefore the unit of your answer is going to be a 9. So I can immediately see out of that list of 6 numbers that the square number, if I know one of them is square, must be 531,441. I can't really remember what I squared to achieve that. I think it was 729 or something like that. But if you square root that on a calculator, you will see that that's got a nice square root. Hence, it's described as a perfect square. The other 5 numbers can't be square numbers because they end in 2, 3, 7 or 8. No square number can end in 2, 3, 7 or 8. So there's a little trick for you. Now I want you to hold on to that idea of how the final digit of a number will be important in recognizing what has been squared and what has been cubed, because we're going to use that technique to perform rapid cube root extraction in the next slide. Now have a little look at n cubed and then certainly pay attention to the unit digit of n cubed, because you may notice that most of the time the unit digit of n cubed is exactly the same as n. Yeah? Now that's not the case for 2, 3, 7 or 8, so you might want to quickly ignore in your head the lines for n is 2, n is 3, n is 7 and n is 8. Because if you look at the lines for n is 1, n is 4, 5 or 6, or n is 9 or 10, you'll notice that the unit digit of n cubed is exactly the same as n. That is going to be really useful to us. Now make sure that you can recall the first 10, actually you'll only need the first 9 cube numbers, so I need you to be absolutely instant on what is 6 cubed, 216, what is 8 cubed, 512, what is 7 cubed, 343. That may at first sound like a very difficult task, but believe me, it's not. You can ask a bright year 8 class to do this for homework, just learn the first 9 cube numbers, ask them to come in the next day, test them on it, and the vast majority of them will be able to do it. And the ones who can't quite do it will only be making the odd mistake. Anybody can learn the first 9 cube numbers, there's no excuses as far as I'm concerned, and that's what I say to the students. So make sure you know those first 9 cube numbers, and make sure you recognise that fact about the unit digit of n cubed. Also pay attention for when n is 2 and 3, we get the unit digits of 8 and 7. And when n is 7 or 8, we get unit digits of 3 or 2. Notice that if we do 10 minus n there, we get the unit digit of n cubed. We're also going to use that in our next trick. So, in the next slide, I'm going to include a little video showing you how I perform rapid cube root extraction. We're about to cube root our 6-digit numbers, or 5-digit numbers. Now, I want to make it clear, I've written down the cube numbers down the side here, just to make it easy for me to explain. But normally, these should be in your head. Obviously, this trick is simple if you've got the cube numbers written down there, but looks far, far, far more impressive if this is all done in the head. And that's why I say you need to know the first 9 cube numbers. Okay, anyway, let's get started. So what I would normally do in a class is I would show them the trick first and demonstrate it, and then I would try and get them perhaps the next lesson. What I normally do is I show them the trick and I explain how to do it. Normally in the lesson previously I've got them to learn the 9 cubes, and then I see if they can do it as well, but they must know their 9 cube numbers. So let's say I ask little Johnny sitting on the front, I ask him to cube a 2-digit number. Now actually that is fraught with difficulties because sometimes they don't understand what 2-digit means, sometimes they don't understand what cube means. Make sure you're doing this in a lesson where you've very, very, very recently gone over what a cube is and what a 2-digit number is. But yeah, so I've asked him, he's using a calculator obviously, he cubes a 2-digit number, and then I would ask him for the answer, and I would tell him I know the first 100 cube numbers and I'm going to cube root it for him instantly. Now the fact is I don't know the first 100 cube numbers, I certainly don't know them, but I do know a trick for cube rooting. So anyway, he tells me the answer is 287496. Okay, and I'm going to try and cube root that in my head. Well, I can do it instantly, and I can tell you the answer is going to be 66. Now the reason that is is firstly the last digit. The last digit here gives away what the last digit was, which he cubed. Now, do you recall me saying that for 1, 4, 5, 6 and 9, 1, 4, 5, 6 and 9, the final digit is the same as the number you're cubing. That tells me that the number he cubed must end in a 6. Yeah? The first digit is a bit more difficult. Always ignore the last 3 digits. We're going to ignore these now to determine the first digit of what he cubed. And I'm just going to look at 287. And I'm going to look at where it appears in this list. And I'm going to think to myself, well, 60 cubed would have been 216,000. So it must be a little bit more than 60. But it's going to be less than 70 cubed, because that would have been 343,000. So really all I need to do is look at 287 and round down. It must have started with 6. And so 287496 cube rooted is 66. 66 cubed is 287,496. And that is the trick. Now let's practice it again, because it's never straightforward. You need to see it a few times. Let's say I got him to cube root a 2-digit number, and Annie, who's sitting at the back, has picked up a calculator and cubed a 2-digit number and come up with the answer, 91,125. And she said to me, Mr. Nichols, and that's my name, what is the cube root of that number? Well, once again, the final digit gives away the last digit, because provided it ends in 1, 4, 5, 6 or 9, it will be exactly the same as this number here. We'll deal with the other case in a second. So I know it ends in a 5. Then ignore the last 3 numbers and just look at the first 2. Well, 91 appears in my list between these two. Always round down to 64, go across 4. I know it's going to be 45. 45 cubed is 91,125. And it's done. Okay, let's say instead that I got the number 54,872. So I've asked a student to cube a two-digit number, and that's the value they've given me. Well, if I look once again at the last number, this time it's a 2. Now 2s, 3s, 7s and 8s are slightly more problematic when they appear on the end. But it's okay, because 2 maps with 8 just as 3 maps with 7, and 7 maps with 3 just as 8 maps with 2. So all I need to do is 10 minus if it ends in 2, 3, 7 or 8, giving me 8 at the end. I now know it definitely ends in an 8. Once again now, ignore the last 3 numbers, look at the first 2 numbers, see where it appears in your list, go down, go across. I can see it's going to be 38 cubed. Okay, let's have just one more go then. Let's have just one more go. Let's say I've asked Isabel this time to cube a 2-digit number, and she's come back on her calculator and told me it's 185,193. Well, once again, we've got one of the problem numbers on the end, but that's okay, because 3 maps with 7, we just do 10 minus 3, and we see it's going to end in a 7. Then I look at 185,000 and I think, well, that would have rounded down to 125, which goes across to 5, and so I know that the answer is 57. 57 cubed is 185,193. Now, do practice this trick first with the cube numbers written down next to it so you can see how it's working, and then try the trick without that, memory aid. Like, it really is possible for anyone to do once they know their 9 cube numbers. I hope you found it quite fun. Like I say, it's not in the syllabus, it's just a bit of fun, but I find that students actually really enjoy doing this, and if you can teach them how to do it, and I honestly think it doesn't take long, it can be done definitely within just one lesson, and normally within just 30 minutes of that lesson, but just occasionally reminding them for 5 or 10 minutes in the next lesson and the next lesson after that. And once they can do it, actually they don't forget how to do it that quickly, because it's a sort of trick as well, which they take home and show their parents. They like magic tricks, and I'll show you a few sort of mathematical magic tricks. I'm no magician in any other way, but I can show you a few maths magic tricks if you like. And in fact, there is a very good book which I'll suggest in the extend part of the course syllabus for this module. It's a book by Martin Gardner called Maths, Magic and Mystery. This is where I first learnt this trick, and I'm indebted to Martin Gardner for showing it to me. So yeah, fantastic book if you want to learn a few more mathematical magic tricks which go down well with the students. Okay, I hope you enjoyed this demonstration, and I certainly hope you managed to get to the point where you can do this instantly, and yeah, I hope it's useful in your future teaching career. Bye bye. I hope you enjoyed the little video on rapid cube root extraction. It's just a bit of fun, really. Like I say, it's not part of the syllabus, but I always find it really really interesting and good fun to teach, and the students seem to enjoy it as well. We're now going to move on to a topic which is also pretty tough. Certainly one of the sort of A-star grade questions, if you like, on the GCSE can be on index laws, although there are certainly B grade and A grade questions on index laws they can ask as well. Now let's just remind us, I'm sure you've all seen this before, but let's just remind ourselves of the laws, or rules if you like, for manipulating indices. Okay, first a bit of terminology. We call a number which is being put to the power of, we call that the base, and we call the power either power, index or exponent. All those descriptions, all those words can be used interchangeably. Okay, so you've got what look to be about 8 rules down there. You can sometimes, I've seen the list written longer than that, but also shorter than that. I'd say that the first 3 rules are absolutely critical, and the last 5 rules can really be derived immediately from the first 3 rules. But I would argue that every single one of those rules is actually quite easy to justify. So have a little think to yourselves, how would you justify the first 3 rules? Well, I'll start you off by justifying the first rule by simply saying that if I'm doing a to the power of m times a to the power of n, I'm going to take an example with numbers, and I'm going to say m is 2 and n is 3. So really I've got a squared times a cubed. Now the reason I'm going to add the powers there is because I've got a times a times a times a times a. Well, that is self-evidently a to the power of 5, and that is why we need to add those powers, because essentially powers count how many times a number's been times by itself, and therefore you're going to add the powers. Now, I'm certain you can easily come up with some very good justifications of the next 2 laws, and I would like to challenge you, because I'm sure you'll appreciate this. After you've justified the first 3 laws, how would you justify that anything to the power of 0 is 1? Because that is something, once again, you can tease the students with, have a bit of fun with them and say, yep, anything to the power of 0, what do you think it is? They will inevitably say 0, you will say no, it's 1, they will argue with you, and then you'll have to justify why it's the case. Now, I would argue that the second law down, a to the power of m divided by a to the power of n equals a to the power of m minus n, is very, 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 very useful for justifying that a to the power of 0 is 1. If you like, quickly have a think to yourself and pause the video about how you'd like to do it. I'm about to explain how I do it to you right now. Okay, if I need to justify that anything to the power of 0 is 1, I just use the example of 7 to the power of 2 divided by 7 to the power of 2. So a is 7 in this example, and m and n both equal 2. Well, firstly, I would say if we want this rule to always work, and we certainly do like our rules to work in every case, then what we need this answer to be is 1, because 7 squared divided by 7 squared is 49 divided by 49, and surely anything divided by itself is 1. But if that rule is to work, then I need 7 squared divided by 7 squared to equal 7 to the power of 2 minus 2, which is of course 7 to the power of 0. And so I've suddenly got the strange relationship that 7 to the power of 0 equals 1. And the same thing works whatever number I put in, if I put it in to be divided by itself. So whether it's 5 cubed divided by 5 cubed, or for that matter n cubed divided by n cubed, you can see the answer must be 1 because you're dividing something by itself, and that answer is always 1. So the reason that anything to the power of 0 equals 1 is simply to make that second index law absolutely infallible. It's to make it work in every single case. Now, for very similar reasons, or certainly you can use a similar approach to justify why fractional indices work the way they do. I'm going to leave that as a little challenge for you to think about, because it's always more fun to think about it in your own head anyway, I always believe. So yeah, I'll give you that as a little challenge, and let's move on. Now, I'm a big believer, and you've probably noticed this in this PowerPoint presentation so far anyway. I think, as the Hungarian mathematician Paul Halmos once said, that to learn mathematics, you have to do mathematics. I still, practice maths questions all the time. I find them quite fun, to be honest. You have to really enjoy maths if you're going to want to teach it with enthusiasm. So, rather than listen to me drone on about how this works, why don't you have a go at the following 8 questions. These are all what I would describe as GCSE level indices questions. Try and do them as quickly as you can, but getting them correct, obviously. I'll pause the video, please, by all means. Give yourself a few minutes and try and answer these 8 questions. Now you've answered those, I would like you to have a look at the following 5 A-level questions. Now, I haven't really explained how these work, and some of you may have problems remembering how this works. Certainly, if I'd just come out of if I hadn't done much mathematics for a year or two, as indeed has happened for 1 or 2 times in my life, I would possibly forget how to do these. So don't feel bad. I'm just going to give you a little bit of a hint, and I'm going to say the trick for some of these questions, not all of them, but the trick for example, the first couple, is to change the base so it's written in terms of the same power. That's all I'm going to say. Change the base. Okay, pause this at the moment and have a go at those 5 questions. See how you get on. Good luck. Okay, I'm now going to provide you with a video to me working through the answers of all of those. Don't feel too, disappointed with yourself, or don't stop beating yourself up if you found the A-level questions quite tough. They were designed to be quite tough. If you found it all very straightforward, I am very, very, very happy for you, but I hope it was useful nonetheless, because it's always nice to remind ourselves how these work, and indeed it's always fun to answer a maths problem. So, okay, I will leave you with this video, which I'm going to talk through the answers to the first 8 and last 5 questions. I hope you enjoyed this little presentation on powers and indices, and I hope it reminded you of how these things work, and I even hope it taught you a new trick. If indeed it did, you may have already known the trick, I don't know, but I hope it taught you a new trick of rapid cube root extraction. You will get a chance to practice that, because there is a little quiz sheet in the quiz section of the course on performing rapid cube root extraction. Okay, all the best, and I hope you enjoyed it, and I will speak to you very soon. Bye-bye. Okay, hello again. I'm going to go through the answers then to those 8 questions that I gave you from GCSE, and also the 5 questions I gave you from the A-level syllabus. Let's see how we got on. Okay, so we started with a cubed times by 4a squared. Now, I've thrown in a number there just to confuse you, and certainly the GCSE paper will do that. We can essentially just ignore that 4 and do a cubed times a squared, which is a to the power of 5, and then times by 4 at the end. And that's because multiplication is commutative. It doesn't matter which order you multiply things in. 2 times 3 times 4 is the same as 4 times 3 times 2. That's a remarkable property if you think about it, because we can do a times a times a times a times a, which gives us a to the power of 5, and then we can times by 4, because provided it's a product, a series of things being multiplied together, it will, simply you can multiply those parts of the product in any order you like. Okay, question 2 was 24r squared divided by 8r to the minus 2, and I hope you could see how I was being a bit sneaky here. 24 divided by 8 is obviously 3. We can do that separately. R squared divided by r to the minus 2, well, we're going to have to subtract the powers, but naturally, because we're doing 2 minus minus 2, the answer is going to be 3r to the power of 4. So you can see in all these questions, I have made them quite tricky. I'm trying to catch you out. But that's just me, I'm mean. That's what I certainly say to my students. Okay, so the next one, 3p squared to the power of 4. Is another good example of questions which students occasionally make a mistake on. What they normally do, they sometimes forget that when you've got a power of a power, you need to multiply it. So they might write that down as p to the 6 rather than p to the 8, which is what it should be. But a very common mistake is forgetting to also apply the power of 4 to the 3 here. And so make sure you have done 3 to the power of 4, which is of course 81. Okay, the next one was 9y to the minus 3 multiplied by y cubed. Now I see a couple of different types of mistakes here. Firstly, sometimes students read this as almost like 9 plus y to the minus 3, and so they multiply the 9 by y cubed as well as the y to the minus 3 by y cubed. It doesn't work like that because once again this is a product, and I point out that 5 times 3 in brackets times 2, well, we don't double the 5 and the 3, do we? We just double one of the 5 or the 3, because 5 times 3 times 2 is in fact 30 and not 60. So anyway, the correct answer to this should in fact be, well, a 9 just stays there, y to the minus 3 times y cubed becomes y to the power of 0, and I would never leave my answer like that because obviously anything to the power of 0 is 1, and so really the answer is just 9. There's a good reason for that as well. If I can just quickly show you over here, this is really 9 over y cubed in the brackets multiplied by y cubed. Clearly they are going to cancel, leaving just 9. So yeah, there's a lot of different ways you can look at that one to demonstrate the answer. Okay, 4 to the minus 3. Well, classic mistake here is to see a negative power and make the answer negative. They love, if they see a negative, they suddenly put the answer as negative. They forget that negative powers have no bearing actually on the sign of the answer. All they do is the reciprocal function, and so this will be 1 over 4 cubed, which is 1 over 64. Okay, I've then started to make it a bit more difficult. I've got 125 to the power of 2/3. Now, one thing to note here, sorry about the appalling handwriting there again. One thing to note here is you can do this in any order, but, and there's a huge but coming, do you know the cube root of 125 squared? I don't know about you, but I certainly don't. I do not know that. So the sensible way to do this is always to root first, whether it's cube root, fourth root or fifth root, and then apply the power on the top. So what I need to do here is 125 cube rooted, which is 5, squared, which is 25. Okay, then we've got the next one. Now the next one I put in because it's deliberately annoying. I like to point out to students that decimals are nowhere near as powerful as fractions. They always disagree. They come away from primary school thinking that decimals are so much easier to use than fractions because they seem to behave nicer in some situations. Well, not when you're starting to do difficult things with them. Actually, it's far easier with fractions. So if you rewrite the 0.25 as a quarter, this suddenly becomes a lot easier. Because a quarter to the power of a half is naturally a quarter square rooted. Now you can square root the top and the bottom. The square root of 1 is 1 and the square root of 4 is 2. So this is in fact a half. And it's done. Okay, the last one was deliberately awkward, but once again they can make it this difficult in the GCSE. If we've got 9/16 to the power of minus 3 over 2, this would certainly be described as an A-star question. I do it in several steps. First thing I do is I apply the negative. The negative is a reciprocal, which on a fraction will simply turn it upside down. So I'm going to say that's the same as that to the power of 3 over 2. I've dealt with the negative now. Okay, now I'm going to square root top and bottom, because that's what that bottom number is telling me to do. So I've got 4/3 to the power of 3. Notice I've dealt with the square root. And now I can cube. So the final answer is 64 over 27. And it's done. Okay, right, let's start again. And let's now have a look at the A-level questions. I'm just going to scrub this. Give me one moment. Okay, so I've got another blank screen again. And I'm going to look at the A-level questions. Now, the secret for all of these is to rewrite the base. the first, not all of these actually, just questions 1, 2 and 5. The parts 3 and 4 I'll show you in 1 second. So 2 to the x minus 2 equals 16 was the first question. I hope you recognise that 2 to the power of x minus 2 equals 16 is exactly the same as 2 to the power of x minus 2 equals 2 to the power of 4. And once we're at that stage, we can do something very, very nice, and also I think natural and intuitive. If 2 to the power of this equals 2 to the power of that, then this equals that. That's the only way they can be equal. So then we have x minus 2 equals 4, and so x equals 6. Now, like with anything you solve in maths, you can check your answer. Is 2 to the power of 6 take away 2, 16? Well, yes it is, because 2 to the power of 4 is 16. And you're finished. Nice and easy. So it looks much more intimidating than it actually is. Same for this one. 128 to the power of x equals 8. Very, very difficult until you write them both as powers of 2. And this is why powers of 2 are really, really useful to know. Okay, so 128 I believe is 2 to the power of 7. If you're unsure of that, just quickly do it on your fingers, yeah? So we've got 2 to the power of 7 there, to the power of x, equals 2 cubed. Yeah, when I say it, do it on your fingers, all I mean is 2, 4, 8, 16, 32, 64, 128. Yep, I'm holding 7 fingers up now. So here we can see from the third indice law from the video that 2 to the power of 7x equals 2 cubed, and therefore 7x equals 3, and so x is 3/7. And it's done. Okay, I'm now going to show you part E, if that's okay. I will show you answers parts C and D in 1 second. It's just that E is very similar to A and B. I probably should have put them all together. Sorry about that. Okay, we had 16 to the 2 minus x equals a quarter to the power of x plus 1. And once again, the trick is to recognise these are both powers of 2. So we've got actually 2 to the power of 4 to the power of 2 minus x. Oh, sorry about that. Equals 2 to the minus 2. A quarter is 2 to the power of minus 2 to the power of x plus 1. Now we can do it. We need to recognise that this needs to really sit in a pair of brackets when I multiply it by the 4. So I'm going to have 2 to the power of 8 minus 4x equals, likewise for the x plus 1, 2 to the power of minus 2x minus 2. And at that point I can say 8 minus 4x equals minus 2x minus 2, and I'm certain you can see from that that x equals 5. Hope it does. Let me just check that. 2x equals 10, yeah, x equals 5. Like I say, you can always check at the end. 16 to the power of 2 minus 5 is 16 to the power of minus 3. Type that on a calculator if you like. And then what's a quarter to the power of 6? Check that you get the same answer. It should be correct. Okay, let me just clear the screen again. Okay, the last two questions which I was going to show you, C and D, are x to the power of a quarter equals 3. And you may have preferred this question, and x to the 2/3 equals 4. I find these can often confuse students because it all kind of happens back to front. Because this is saying the fourth root of a number is 3. Well, that means we have to go backwards and actually do both sides to the power of 4, so that I end up with x to the power of 1, which is just x, which is obviously what I'm looking for, is 81. The next one is even more awkward in many ways because we have x to the 2/3 equals 4. Well, this means a number cube rooted then squared became 4. So really what we need to do is square root then cube to get 8, which is going to be our answer. The way you can notate that is to think of it as, well, I'll do this to the power of 3 over 2 because 2/3 times 3 over 2 is 1. Which means I need to do 4 to the power of 3 over 2. That gives me x to the power of 1 is 4 square rooted, which is 2 cubed 8, yeah? They kind of work the opposite to when you've got x as the exponent. Because x, the unknown, is the base, it makes it just slightly more confusing. Anyway, I hope that was a helpful reminder of the wonderful world of powers and indices, and yeah, I hope you really enjoyed the presentation this week, and in the end you find it very useful in your teaching career. Bye bye.